So yeah, welcome to my talk where I'm going to be sharing with you some fun that I've had with regards to hunting Android malware. So who am I? I'm Chris. Hello everyone, nice to meet you. How awesome is BruCON? That's your cue to make some noise. You don't have to, don't worry, we can just keep awkward silence. I can roll with that as well. But yeah, hacking and beer, like two of my favorite things, so can I stay? So I'm Chris Leroy. I'm a security engineer / researcher. I use those two terms very loosely, but generally I just like breaking stuff and building stuff. I work for a company called Heroku, and yeah, you can find me on Twitter, Brompuani, if you are on that side of the cybersphere. So enough about me. So a bit of an outline. This is more for me than it is for you, just so that I don't digress from what it is that I want to share with you today. But this is what you can expect in the next 40 minutes or so. So we're going to look at a problem that I saw at some point, an interesting question that I was asked that triggered an idea that I then created a POC, which led to some interesting results, and there is a bit of a conclusion. So what is the problem? I don't think this slide is a surprise to anyone in this room. Android and malware, those two fit together very well, and it's a problem that we've been dealing with for quite some time. These are just some of the headlines from the past year, and this has been happening for a long time on a very large scale. So not really new, but when I started dabbling in reversing Android malware, I wanted to see how easy it was to actually create some of my own. So the research that I'm actually going to be sharing with you today is actually derived from some previous research that I did. I created a tool called Quetzal quite some time ago, so that's the very bad ASCII art that you can see over there. It's not a tool if it doesn't have ASCII art, but I must point out that originally this ASCII art was green text on a black background, but in an attempt to break down hacker stereotypes, I changed the ASCII art to white, just so that you are aware of that. So I shared this tool, and it basically just backdoored any Android application with an interpreter payload, nothing really interesting there. And I was sharing this research with some researchers, and we were discussing it, and most of the questions that I got was, well, Chris, how do you backdoor Kotlin apps, or does it really matter? How do you bypass antivirus? How do you ensure stability? So pretty much the usual red teamy, kick every door down kind of question that I got, which is what I was expecting. But I got one question that took me by surprise, and the question was from a developer that was developing Android apps, and the developer asked me, Chris, how do I detect if my app has been backdoored by this tool, or if my app has been infected with some malware, or in general, how do I detect malware? And to answer this question, I spoke around 2 points. So I said, well, firstly, you've got to look at the APK, so perform some sort of static analysis, tear apart that bag of bits and see what it is that it is doing. Then I also spoke around sandboxing. So you want to analyze this piece of malware in some sort of sandbox and see what it does. And this question led me to think about, well, I've created something with an offensive capability, but is there some way that we can detect the usages of this tool? So I figured, well, let's go ahead and see how we analyze malware. Nothing new over here, the usual hashes, code signatures. So this isn't specific to Android or mobile malware. But in Android, it's quite interesting to look at the permissions of Android applications. For example, if that torch app that's for free that turns your phone into a torch, and if it's asking for premium SMS access and your GPS location, that's probably sounding a little bit dodgy, and you'd probably look at that app with a bit more scrutiny. And then the last point, behavior, which ties into this point, but when you're looking at apps, you typically want to look at the apps that appear to be dodgy, the ones that are draining your battery, the ones that ask for ridiculous permissions, so on and so forth. But how are we protected by malware? So quite recently we've had Google Play Protect, or formerly Google Play Bouncer. Some of you may have remembered that. So that's normally that little alert that you'll get on your Android phone saying, do you want to analyze this or submit this application for analysis? And of course there's the Play Store. Now this is quite debatable if it is an effective protection against malware. I'll be happy to discuss this with anyone afterwards. But the idea is that verified developers submit their applications, and you can trust the Play Store to install the apps that they offer. Then, of course, there's third-party software, so good old antivirus. I'm of the opinion that antivirus and the word mobile are oxymorons. So, yeah, I think that's where we stand with that in this field of research. Some OS support, so a lot of the operating systems out there that modify the Android operating system, try to implement some mechanisms to prevent against malware. Android's got this by default, so things like SE Linux, so on and so forth. Then you've got your MDMs and your MAMs, which can try and limit what the users are installing and enforce profiles and enforce passwords and all of that. So those are some of the ways that we're looking at and trying to protect ourselves from malware. But I noticed that there are some shortcomings. So I think static analysis is hard on a good day. But in Android, it gets a little bit tricky because are you going to be looking at Java or Kotlin? Sure, you can look at the smiley level, it's all the same, but then you can run into issues with the different ARM versions that you are looking at. And in general, static analysis is hard. Also the issue that you can't run things like Cuckoo on your phone. If you think an app is dodgy on your device, you have to set up a separate machine, set up Cuckoo, and put the sample there. And of course, there's scalability. And quite recently, the Google Paper Tech team and their researcher Maddie Stone gave a talk at Black Hat. Really cool talk on how they manually analyzed a piece of malware that had some pretty cool anti-tampering. I recommend you look at the talk when it's available. And they had to put an analyst behind the sample to see what it was doing so that they could then implement tools to then automatically detect it. And this shows a pure scalability problem. There are thousands of samples out there, and sure, you can automate as much as you can, but you still need a human behind a monitor to verify or to look at those samples that can't be auto-magically analyzed. So scalability is not on our side. Also, what if the app is not on the official store? So this is quite a big trend. Some apps aren't available in certain regions, so you download third-party apps. And of course, bypassing AV is too easy. Forensics has a very interesting approach. I like it, but how do you use forensics tools at runtime? You have an app that you want to look at, and how do you go ahead and use the existing tools at that very moment in time? It's quite tricky. And then, of course, this last point, and I'll elaborate quite a bit on this going forward, but static analysis can only show you a subset of what the application is doing when it's installed on the device. So we're quite limited to what we can see, provided that we can only see what the APK is doing, which is not always indicative of what it can do. So basically, my main frustration was that on a phone, there's no reliable way to detect malware on devices. So then I had an idea. These are quite rare things, so I was ready to embrace it. There's heaps of data to be looked at, and I do apologize for the really lame jokes going forward, but I enjoy it. And I thought, well, Android apps make use of objects everywhere. And I thought, okay, import statements are useful to look at what objects an app is using, but you can import but not necessarily instantiate. Very bad coding pattern. You can, in a way, assume that if it's instantiated, something is using the object. So if there's my object, mu equals new object, something is using that object, or they're just wasting memory. And of course, instantiated objects have data. They are very interesting to look at. So I thought, well, okay, everything that an app does boils down to objects. So this data has to be sitting somewhere. And we know it's sitting on the heap. And one of the first places we may typically look at is proc PID of the process in maps and look at the heap regions. I'm currently suffering from quite a lot, from significant hair loss. I don't want to lose any more, so I quickly ran away from proc PID maps and thought, well, why don't I look at the HP raw files? And sure, you can look at that, but you'll be fighting with the garbage collector on a regular basis. And if any of you have generated HP raw files to get a snapshot of an Android process, you'll notice that time is not on your side. And sure, you may get it a couple minutes or a couple seconds afterwards, but it's also quite tricky to work with HP raw files. So then I thought, well, what about memory forensics? They're a really cool tool, so LAM or volatility. So you either require a root on the device or a customized kernel. and you can get a nice snapshot of the device's entire memory. Not exactly what we were looking for, because we were looking for the memory for specific processes, but in this case we can get everything. The last point is my favorite, good old GDB to the rescue. So on older Android devices, so Android 4, when we're still using DL-malloc, if you go to any object and you say get hash code, you can get the base address for the object. And if you go ahead and then read the bytes, 20, 40, 30 bytes from that base address, you'll actually see the object. And you'll see the magic strings that identify that object. Really cool for older Android devices that were using DL-malloc, but on ART it's something different that I won't go into now. But yeah, if you like JE-malloc and ART, it's quite interesting. So these are some of the ways that I was like thinking, well, yeah, let's look at the memory, let's look at what objects are there. And I got really frustrated and nothing really worked. And then I thought, well, what about instrumentation? So there's this great tool called Frida. Not the only instrumentation tool out there, but I thought, well, these objects exist, so they must be on the heap, and therefore they must be accessible. Not only with instrumentation can we access the objects on the heap, we can also trace calls and monitor behavior. And Frida's made it relatively easy to implement this compared to the previous tools. And it's a great way to gain insight into applications in general, not just for analyzing the heap. But why I stuck with Frida was because its object carving functionality is awesome. And I will show you in a bit why. So I thought, great, well, we've got instrumentation. It's providing a mechanism for me to look at the heap in quite an efficient way, so I don't have to try and integrate with GDB or start processing the heap regions. So I thought to myself, wouldn't it be cool if at runtime I could see which objects an app is using, which objects are instantiated, and what are the values for these objects? Because if I get this information, this would give me an idea as to what an app is doing and how. Because everything that an app does boils down to some sort of object somewhere that does something. For example, if I were to analyze an application that was, say, hypothetically backdoored with an interpreter payload, experience tells me to look for two things. A DEX class loader, which is used to inject jars or APKs at runtime for additional functionality, or to look for a TCP connection, because I know that interpreter can only establish connections over HTTP or TCP. If I see these objects, this tells me that the app is injecting code at runtime, and it's communicating remotely. Relatively simple. So going forward, we're going to use a infected app because it's quite fun to infect apps, I think. And I'm, sorry, on the wrong slide. The play button I need to find. Computering is hard. I apologize. There we go. So we're just using a stock standard interpreter backdoor, using a standard multi-handler, and what we've gone is just backdoored a version of Twitter, and we get a session, and all that we're really going to do is just perform some malicious activity. So we have an interpreter session, we have remote control of the device via the backdoored application, and we're just going to go ahead and take a screenshot once the super secret password. The reason why we can do this from this infection is because our interpreter session is running in the context of the Twitter application, and because it's itself, it can take screenshots of itself. Just in case you're wondering, there was no magic there. And yeah, we go ahead and we take a screenshot, and we have an infected device. So that is the sample that we're going to work with. So we have this, and how do we actually analyze this malware using Frida? I apologize for the small text. I see that now, but the videos are up online, so you're just going to have to either squint really hard or see the videos afterwards. But what we're going to do now is use the Frida JavaScript client, and we're going to look for some particular objects at the top. So we have java.net, .socket, and DEX class loader, and here we're using Frida's object carving mechanism. So what we're going to do is we're going to scan the heap for instances of particular objects. If we find an instantiated object, we're then going to display the details for that object. We're then going to attach Frida, which is using ptrace, to a particular process. In this case, it's the Twitter application. And basically what we're going to say is, hey, scan this application. If you come across an instantiated object of java.net.socket, display the contents. So you can see over here, we have a whole bunch of instances of java.net.socket, which are basically showing all the remote connections that this app has made at this point in time. So there's a whole bunch to twitterimage.com. You can get the local ports and the remote ports. You'll see this one over here is actually our interpreter connection, because we have a remote connection to a 192.168 range on quad 4. And what's quite interesting as well is at the bottom we have two instantiated objects of DEX class loader, which means that this application is loading two jar files into the process at runtime to inject additional functionality. And we can see it right here. We can see that the jars have been placed in data.com.twitter.android and has loaded those jar files, which were then loaded remotely from the multi-handler. So this is how we can use Frida and its object carving to look at an app at runtime and say, hey, tell me what objects are on the heap, what have been instantiated, and what are the values of these objects. So this is quite fun to run this script onto a lot of Android apps, and yeah, you see some interesting results. So I mentioned earlier that static analysis won't show you everything, and what it won't show you is runtime injection. For example, the jars and the APKs that are loaded from DEX class loaders, if you get access to the original APK, you'll see reference to DEX class loader, but you won't be able to see the contents of the jar or the APK because it's not included if it's loaded remotely. So you're not going to see this data. And typically, if you pull off an APK with ADB, you're going to get the original APK, but you're not going to get the content that's in data.com.twitter.android because the sandbox permissions won't let you. So generally what we do to get access to these third-party APKs is run the app in the sandbox on a rooted device and then gain access to it. But by default, you won't get that. Then there's my least favorite Java package, java.lang. And what's interesting about this is that every Android process will get an instantiated object of all the classes in java.lang. So there are no import statements, and this becomes interesting if any of you know the Java space, runtime.exec. So if you want to run any shell commands or get a reverse shell or anything like that, runtime.exec is going to be the command that you're going to run. And what's interesting about this is that you don't instantiate runtime, it's static. You get granted a instance, and I say it's kind of immutable because you don't have control of the properties that get set. The properties typically get set by the actions that you perform on the object itself. So it gets a little bit tricky when you want to dump the contents of the object and see what it's actually doing. So let's go ahead and actually look at an example. So on the left, we have an Android application. I'm going to run it in the debugger so you can just see the code. So on the left is a vanilla Android application, hello world. Then on the right, we have some Java code that we're going to bundle into a jar and then execute at runtime on the app on the left. So if we were to perform static analysis on this application on the left, this is what we would see. We would not see this code unless we got access to this additional APK. So we're going to load it up, and we're then going to use our script that we were using earlier that's going to scan the heap for all the instantiated objects of a particular type and then dump out the contents. So we're going to break at these points. Once again, I apologize for the really small text. If you can see that, that's impressive, but I do apologize for that. But I'll tell you what's happening, and I guess you're just going to have to believe me. So we're going to run our script to scan the heap at this point. And here we're looking for DEX class loaders or java.net.socket objects and a bunch of other objects. And we can see we get nothing. If we step over a couple other points, what's going to happen over here is we instantiate an object of DEX class loader, which we can see just appeared over here on our script. We're instantiating this because we want to load this jar into memory at runtime to execute all the functionality that's in here. That's a great way to hide your functionality. And once we have the instantiated object, we're then going to iterate and actually perform some methods on the object that we have via reflection. So there's a method here called makeBeard, and it's just two out.printlns, which are over here. and those don't have any particular objects of interest. There's one command that we did run, which is then bin ps. So we can see in our ADB output, ADB logcat output, we have the output over here, so it executed. If we then actually go ahead and run our script to try and analyze the heap, we'll see that we actually won't get anything because runtime object is really difficult to tell if something's been executed on it. But we'll look into that solution in a bit. The next method that we execute via reflection is over here, and what it's going to do, it's going to establish a HTTP connection, which is this code over here. So once again, this code has been loaded into memory via the DEX class loader. And we're going to run this method, which establishes an HTTP, TCP connection and executes an HTTP GET. When we then run our script, we'll get some information, and of course we'll get an error because you're not supposed to do HTTP GETs in the main thread of an Android app. And when we then run our script, we will then see two instances of java.net.url and java.net.socket, which shows that the code that we ran here, you can't see over here because it's been loaded at runtime, but our object carving at runtime has identified those two objects on the heap, which shows us that if you're performing static analysis on this application, you would not see this. So I have heaps of love for this approach because you don't have to troll code. You can programmatically specify the anomalies that you want to identify, which is pretty cool. For example, you can say, scan this code and tell me if these objects exist, and if they do A, B, and C. But there's also some frustration. So like I said, java.lang.runtime, every Android process will get an instance of this object, and this is what it looks like if you were to inspect it in a debugger. If you wanted to try and detect if some process has executed system bin ps or executed runtime.exec, if you were to analyze that object, there's not an easy way to see, oh, someone executed that. So it's really not very useful to look at. But we have instrumentation that we can use, so what's the plan? So according to the documentation, I apologize for showing you Java docs at this time of day. You can go have plenty of beer after this. But for once, the Java docs were useful and said, hey, there are 6 unique signatures as to how exec can be executed. And what we can do is we can overload those signatures for a particular process, which basically means that every time any one of those methods are executed on the exec object for a particular Android process, we can intercept that call and then see exactly what's going on. So what does it actually look like? So once again, I have an app over here, and what we're going to do is we have a script over here. All it's going to do is attach onto the process, overload all the exec methods, and essentially what's going to happen is that every time exec is called on this process's runtime object, we're going to intercept it, essentially see what is being sent to the method, and then pretty much identify that a specific shell command was executed. So we go back to our victim map, and we are running this code from a jar that has been loaded into memory. So we're going to run these commands, which are over here. Once again, I don't expect you to see this, but via reflection, we're going to execute the commands that are from our jar that we've loaded via DEX class loader. So once we load up our emulator, and we'll see the particular code. So we'll see the command there is bin sh. So we should see that being sent through to the method signature. When we click run stuff, you'll see that over here, our script, when it ran, some stuff popped up over there. And what's happening over here is that it's saying exec got called. So that means that this process was running the exec method on a particular object. It's all very fun. But how does it work if we maybe wanted to run it on an infection? So we're going back to our infected Twitter application, and what we're now going to do is run the same method over here, but we're going to see how Meterpreter executes shell commands, and it's quite interesting. So we have our Meterpreter shell over here, and if we run an ls, we'll see that we are in data com.twitter.android, but our script didn't fire anything. So that means that that piece of functionality isn't using runtime.exec. But if we drop down to a native shell in Meterpreter, we can see that there was a call, and the call that was sent to runtime.exec is sh -csh. And those of you who are familiar with Java reverse shells, that is the command that you would typically want to execute. And we can see now this now has established a pipe, and we've got an interactive shell on the Android device, and all the commands that we'll run, you'll see that Meterpreter doesn't create a new exec method every time. It's established a pipe. So all the commands are just being piped through to the instance on the other side. And if we kill this instance and create another one by typing in shell, we'll then see that we get some information over here. So this is one way to identify if an Android process is executing shell commands. Typically, it's not the kind of stuff that you would want to see on your device, but you can go ahead and see it at any time. So if we just take a snapshot at this point in time, we have the ability to analyze the objects on the heap. We can hook methods for certain objects and method signatures. We can do this all at runtime on a device. So no need to take memory snapshots, take it offline and process HP raw files or volatility snapshots. We can see more than static analysis. So static analysis and this works really well. And we can perform the above from a workstation, which is ideally not what we want to do. We want to run everything on an Android device, which then leads me to the safety net attestation API. So when I thought of this functionality, I said, well, Android has this really cool feature called the attestation API, which from an Android app, you can programmatically query the state or the awareness of the Android device. For example, is it rooted? Is it using a proper version of Android? So on and so forth. So it exposes an API via the Google Play services. So I thought, great, well, there's an API in the Android operating system to query this information about the environment that the app finds itself in. Well, wouldn't it be cool if there was an API that could give you information about particular apps? So I thought, well, according to the architecture diagrams provided by Android, you can see that the SafetyNet Attestation API lives inside the Google Play services. And I thought, well, you could potentially slot something in over here to provide an API to provide information on Android applications. And that then led me to develop something called 8Cake. And you can use this API to analyze applications that are installed on an Android device. It's a custom Android Frida library. It's essentially dbus over TCP, yes, on Android. It is as ugly as it looks, which then provides us with Frida server integration with the Frida daemon. This can run all the tests that I showed you previously and more. For example, if you were to say from your workstation, hey Frida, give me a list of running processes, this is typically the command that you would run from your workstation using the Frida client, and that's the information that you would get. If you were to do this from an Android device, so from your Android application, you could do something like this. Instantiate an object of 8Cake utils and say, give me a list of all the processes running on the device using this particular method. And this is all done within an Android application. Similarly, for looking at processes, you could say, hey, Frida, tell me if this app looks malicious. So remember previously we had a script that was living on our workstation, which we then called from the Frida CLI, and that gave us that juicy information. How would we do this from an Android application? You can do it like this. Just give it the Frida host and Frida port. So what I was doing at this time, because Frida is not a native daemon in Android, I was just building custom Android ROMs with Frida bundled in and flashing it onto a Nexus and then exposing it on a certain interface, which is a terrible idea, but just to POC it, that's what I did. And you just specify a IP address and a port and the PID of the process that you want, and those tests that we ran previously would go ahead and be executed on that process that is running on the Android device. So why the 8Cake API? So there was no Android Frida library to demonstrate this. It didn't exist. I wanted to use Frida because its object carving capability worked really well. I didn't want to go ahead and implement some GDB integrations. I wanted to keep the little hair that I have left. And I wanted a client-server model that aligns itself with what currently exists with the attestation API. And lastly, the most importantly, I didn't want pain, because if you go to the dbus documentation, that sentence over there, if you use this low-level API directly, you're signing up for some pain. So basically what I did was I didn't implement the dbus protocol. I did something else to avoid the pain. So if you look at 8cake, you'll see a lot of these, you'll see a lot of byte arrays, and basically all that it is a TCP socket to the feeder daemon, and just pushes and pulls a whole bunch of bytes. Where do these bytes come from? Well, in the beginning, I did not know the debug specification at all, and I still don't know it. But what I did was I just sniffed sessions between my workstation and an Android device when I was using Frida, and basically performed a replay attack to see if this could work without going through the Frida CLI, and surprisingly it did. All that I really then did was outline certain key fields. So for example, you're not going to be analyzing the same PID all the time, you need to change that. You've got to identify some key bytes that feeder and dbus needs to communicate, and wash, rinse, repeat. So if you look at 8cake, you'll see a lot of byte arrays. What some of them do, what some of them mean, I have absolutely no idea. If anybody here knows, I'd love to know more about that. But how it looked as a first POC was this. So this was the initial research, literally copy-pasted bytes from Wireshark sessions. And if you're familiar with dbus, you'll see the auth preamble over here, and then basically just sent bytes between the feeder daemon from existing sessions that I had sniffed, and it actually worked, quite surprisingly. I don't know why I'm surprised about that, but not the most reliable when using Python, but when ported over to Java and Android, it was actually quite reliable. So where can you get it? It is all out on GitHub. So the feeder scripts, if you want to execute from the workstation, are there. The Android library is there as well, so you don't have to worry about compiling the code. You can just embed it into your Android application. You just got to make sure that there's a feeder instance running on the local device. There are also the sample apps that I was showing that are also running there. And yeah, the videos that I've showed you are also at this link. I think you can trust this URL. It's the one that Google gave me, so that's where you can get everything. But with all good research, there are often shortcomings. So this definitely, if it were to be implemented, would definitely increase the attack surface, because now you've got something that is reading the memory of Android applications, which just absolutely terrifies me at the same time. So this process would typically run as root, and what do we know? Services running with privileges like that would be targeted. And the pessimist in me is saying, well, we're still struggling to get basic security right. I don't know how I feel about us implementing a mechanism in Android that's going to allow some service to scan the memory for Android applications. Like I said, it is quite terrifying. So, some of the conclusions from this so far. It's a journey that I've seen so far. I don't think it's a silver bullet at this point in time. I think in conjunction with all the other mechanisms, it's a step in the right direction. Defense in depth is key with all of this in the Android ecosystem. Malware is a problem. Dynamic analysis in conjunction with static analysis can be really powerful to help you understand what an app is doing. But I do believe that the Android operating system is key to protecting itself, because third-party applications are limited by the capability that is provided by the API. So you can't have system access if you're a third-party app. So the Android operating system has to provide that. So as the end of my presentation, I have flown through it, and I've actually realized now it's because I've actually missed a couple of slides that did not make in my last edit that actually showed the 8cake demo. So what I'm going to do is actually just open the floor up for any questions if there are any. Cool, so yeah, I did miss out one slide that shows 8cake running from the Android application. It is online. You'll see that the application uses the library, and then you specify a particular process that you want to analyze, and it'll go ahead and tell you, hey, this app is using DEX class loaders, this app is using these objects to establish these remote connections, and it can be quite useful. And you'll see why I'm not a developer just by looking at that application. But if you do want to see the actual POC, it is running there and it is all online. So yeah, thank you for your time. See you at the party. Don't drink too much. And yeah, have a good one. And thank you, BruCON, for having me.